How's it going, guys? Welcome to another video on matrices. Today we're going to have a look at chapter 8.6, talking about dominant and communication matrices. So starting things off, we've got what's called rearchability. Now, rearchability is basically the concept of how it's possible to go from one vertex in a directed network to another. So I've got the example here where we've got three towns, town A, B, and C. So we're going to consider the possible pathways or routes going from town A to town C. So what are the different ways? So starting with town A over here, well, we've got two lines or two pathways that go directly from town A to town C. So two pathways directly from town A to town C are considered what's called one-stage pathways. We can go directly from one to the other. However, we can also go from town A to town C by going through town B. So here's one example. I go from town A to town B, and then from town B to town C. The other option is I go through this pathway. So town A to town B, and then from B to C. So there's another two pathways I can go from town A to C going through or via B. So these are called two-stage pathways. And the pattern continues. So if I had a town D over here, and there was another pathway that went from town B to C, well, that would be a three-step or three-stage pathway, because I would go from town A to town B, and then from town B to town D, and then from town D to C. So there's three steps, so three-stage pathways. I'm not going to do that though. We've just got this situation where we've got just three towns. So the other thing to notice is there's no routes entering town A, but there are four leaving it. So see the little arrows on each of the pathways indicating that's the direction the path goes. So I can't go from town B to town A because there's no pathway that goes that direction. So we say the in degree of A is 0 because there's no pathways going into town A, whereas its out degree, meaning it's going out of town A, there's 4. So there's 1, 2, 3, and 4. So the next thing we want to look at is how can we represent the two possibilities, or the one-stage and the two-stage pathways for a directed network in matrix form. So when we actually make it into matrix form, we call it the adjacency matrix, and we denote that by A. So again, consider the town A, B, and C, and there's all our pathways. So what we want to work out is the one-stage matrix. So we just need to fill out a matrix. So we've got going from town A, B, and C, and we're going to town A, B, or C. So how many different ways can we go from town A to town A? Well, there's no possibilities. If we had a situation where there was a pathway that looked like that, that would indicate that we're going from town A to town A. Doesn't do much for us, but we don't have that for now. So from town A to town B, well, there's two different pathways there. And from town A to town C, well, there's two pathways there. Again, we're considering the one-stage matrix, so there's only two possible ways we can go from A to C at the moment. Next one is looking at town B. How can we go from town B to town A? Well, there's no possible ways because we don't have a directed path to A. From B to B, again, there's no possible ways to go there. And then from B to C, there's one. From town C, I have no possible ways to go to any of the other towns because all the other pathways are going into town C. So it's all zeros along the bottom. Okay, so just tidying up, I can call matrix A as that. So that's the one-stage matrix. The next thing we're going to look at is the two-stage matrix. So again, same situation, we've got A, B and C going from the towns to the other town. So two-stage matrix. So how can I go from town A to town A? Well, there's no possible ways I can do that. Again, because I can't make a loop. So if one of these were going that direction, I could go, well, A to B to C, back to A in that case. But at the moment, I can't do that because there's no pathway going back that way. From town A to town B, for the two-stage matrix, well, I can go to C. There's no possible ways to go back to B. These are one-stage matrices or pathways. So again, there's no pathways for the two-stage matrix. From A to C, I can actually go to A to C via B. So 1, 2 possible ways there. I'll just outline the two different spots. So we've got 1, and so there's 1, and the next one would be that one. So even though we use this pathway twice, that's okay because we've got two different possible ways or paths over here. From B to town A, again, there's no way to go back from C to A, so there's no possible ways there. From town B to town B, I can't make a loop. I can go to C, but I can't go back to A, so there's no possible ways there. From B to C, I can go directly there, but that's the one-stage pathway, so there's another 0 there. And then, like before, we've got no pathways that go out from town C, so they're all zeros. So the two-stage matrix I actually represent as A squared, and we just fill in the numbers as followed. Okay, so that's the two-stage matrix. So a fair bit of definitions to start with. So we're looking at what's called the dominance matrix. So we're looking at what vertex or what town, in our example before, has the most influence over the other towns. So if an edge in a directed network moves from A to B, then it is said that A is dominant. Okay, it's moving from A to B. A is the dominant matrix. So it's more dominant over B. If an edge moves from B to C, then B is the dominant matrix. So B is dominant over C because we're moving from B to C. So sometimes we want to find out what the most dominant matrix in a network is. So what vertex holds the most influence over all the other vertices? The dominant matrix is usually found by inspection. So if we go back over here, which town has the most influence over the others? Well, it looks like town A because we're going from A to B. Okay, there's two different possible ways. So in this case, A is dominant over B. It's also dominant over C as well because we're going from A to C, A, and there's two different possible ways. Overall, A is going to be the dominant matrix. So you're looking at where it starts, where does it end, just by inspection. However, we do need to find a more formal approach to finding which vertex is more dominant over the others, and we use that by we find that by using matrix representation. So generally speaking, if there are more ways to go from A to B than there are to go from B to A, then A is the dominant matrix. That's what we're looking at. So consider the following two matrices. When you look in the next video where I go through the examples, these matrices are found in example 14. don't worry about that at the moment. Just consider we've got two matrices, and for the example, it might be 4 towns, so A, B, C, and D. So A, B, C, and D. A, B, C, and D. Okay, which town is the most dominant over the other? That's what we're looking at. So to work it out, we take the sum of each row in this matrix. So what we want to do is basically add them two together. So here's our one-stage matrix, like we did before, finding out all the different pathways. This is the matrix we obtain. This is the two-stage matrix. So for this element here, I can go from A to C two different ways for the two-stage. That's what it's looking at. So what we want to do basically is just add them together. So we've got one stage and two stage, add them together, what do we get? So just matrix addition, so we'll get 0, 2, 1 plus 2, which is 3, 3 and 1, so 4. We'll have zeros there, a 1 and a 2, 1, 1, 2, so 0, 0, 0 and 1, and then zeros along the bottom. So that's what we get when we add them two together. So to find the dominant matrix, it belongs, basically the dominant matrix is the one that has the highest sum in them, each of the rows. So once we've added them together, add all the elements up. So 2 plus 3 plus 4, you'll get 9, 1 and 2, which is 3, 1 and 0. So what we can say is row 1 is the most dominant, or it has the highest number, so vertex A would be the most dominant. It's more dominant over the rest. So that's how we find the dominant matrix. Okay, so I'm going to end the video there. In the next video, I'll go through some of the examples. So stay tuned. Thanks for watching.